So now we're going to talk about definite integrals. And by that, symbolically, maybe we'll look at something like this. So we're looking for the integral, but for particular values of x. So we know we can find the antiderivative of x squared. That's going to be 1/3 x cubed. And we'll leave off the plus c for now. Given this, we know we've got the graph of x squared, and what we're looking at is finding the area under the curve, and we're looking specifically between the points where x equals 1 and x equals 3. So this area here. So what we're going to do is, technically how we find this is by saying, so here symbolically, here's what we say. So there's the antiderivative, and we're taking it between the values of 3 and 1 for x, and it's simply taking the antiderivative when x equals 3 and subtracting the antiderivative when x equals 1, or 9 minus 1/3, or 26/3. Now, how does this work out? So we said before that the integral, or finding the antiderivative, tells us the area underneath the curve. So if we're taking specifically this area between x equals 1 and x equals 3, let's think about what we've learned so far about finding the antiderivative and using that as some measure of area beneath the curve. So in general, before we thought, okay, well, the area under the curve x squared is the antiderivative, so 1/3 x cubed, and we looked at it between 0 and 3. So if x was 3, the area under the curve of x squared was going to be 1/3 x cubed, or 9. If x were 7, it would be 1/3 7 cubed. If x were equal to 5, 1/3 times 5 cubed, etc. So in this particular case, if we think of the area under the curve between 0 and 3 above the x-axis, we're looking at this entire area here. Okay. If we're only looking at the area between 1 and 3, we're taking, we can think of this entire area between 0 and 3, and we're subtracting this area here. So this area right here between 1 and 3 it's simply the area between 0 and 3, and we're going to take away this area that's less than 1. Well, what's this area right here? Well, it's the area under the curve between 0 and 1, or 1/3 x cubed. So the entire area would be the area between 0 and 3, or 1/3 x cubed. The area between 0 and 1 is 1/3 x cubed. So the integral, the antiderivative, the area under the curve between 1 and 3 is simply this value minus that value. Let's look at another example. Maybe a little more straightforward. So we've got f of x equals 2x plus 1. Its antiderivative, or if we take the integral, what's the area under this curve? It's going to be x squared plus x, plus our constant. And again, checking, we've got the derivative 2x plus 1. Here's our graph, something like this. This is 1. In general, we can find the area under this curve. If x equals 5, we've got the point, oops, 511, and we've got a triangle, and then we've got a rectangle, or we've got a trapezoid. We can find the area under that curve. Well, what if I only want to find the area between x equals 2 and x equals 5? So this area here. Well, I know from what we've done before, the area under the graph between 0 and 5 should be x squared plus x, and when x equals 5, that would be 5 squared plus 5 equals 30. Well, I don't want this area down here when x is less than 2. So the area under the graph between 2 and 0 would be, again, x squared plus x, or 2 squared plus 2. So we should get an area that's 24. So symbolically we would say the integral, or the 2x plus 1 between the values of x equals 2 and x equals 5 should be x squared plus x between 5 and 2, which equals 5 squared plus 5 minus 2 squared plus 2. 24. Now, if we wanted to, we could find area of a small triangle and a large rectangle. This rectangle, here we've got the points 2, 5. So we've got a rectangle whose width is 3 and whose height is 5. And then we've got a triangle. That area would be 1/2 the base times the height. So going from 5 to 11, it's a height of 6. And that would be 9. And in fact, from the graph, we can see that this area equals the area that we find when we find that antiderivative.